Hi and welcome to my talk. My name is Marvin Eisenberger. The title of the talk is G-MSM, Unsupervised Multi-Shape Matching with Graph-Based Affinity Priors. In this work, we address the problem of unsupervised multi-shape matching, which means that we take a collection of 3D shape poses as input, and we want to jointly compute dense correspondences between all of these surfaces at the same time. We do so by first, in a self-supervised manner, constructing an edge-weighted graph on the collection of poses. And then our approach can be essentially summarized as a three-step process. First of all, for this collection, we predict putative pairwise correspondences. We then define these affinity scores in a self-supervised manner. And from this, extract multi-shape correspondences in terms of shortest paths within the shape graph. Yeah, and please refer to the longer version of the talk or come to my poster to discuss more details. Thank you very much. Right, so the task again is to compute multi-shape correspondences, which means that we take a collection of poses as input, for example, these four, and we want to compute dense point-to-point correspondences between any pairs of surfaces in this collection. So now if we look at conventional state-of-the-art methods, they typically compute correspondences in a pairwise manner, which means that during training, any pair of poses are sampled and correspondences are predicted. This has certain limitations as we show in this work. So if we, for example, sample this pair and predict correspondences, then these are the resulting correspondences that a state-of-the-art method gave us. And well, this pair in particular is very challenging because you can see that there is a lot of places of self-contact. And in all of these places, there's actually topological merging of the meshing, which makes it very noisy, very challenging. So in order to address this, we can actually leverage multi-shape correspondences because instead of just computing correspondences in a pairwise manner, we can jointly compute correspondences between all of the poses at the same time. And this tells us something about the latent topology of our collection because yeah, we can somehow infer what places are meaningfully connected and not from the other poses. So again, as I said in the spotlight, the approach is essentially a three-step process. So first of all, we predict putative pairwise correspondences. Then based on these pairwise correspondences, we construct affinity weights. And from these, we will extract the multi-shape correspondences. So to go a little more into detail on all of these three steps, first of all, the pairwise matching. We use a conventional architecture that consists of two components. First of all, the feature extractor, which does some sort of representation learning based on the diffusion net architecture. And essentially, it learns pointwise features on all of the input poses in the training set. Then the second part is a differentiable matching layer, which takes pairs of sets of features for two given poses and outputs the putative pairwise correspondences pi ij. Now, the second part is how to define our affinity edge weight heuristic. We do this using the optimal transport distance of the pairwise feature maps. So essentially what this does is it quantifies how close the learned feature embeddings are under the putative pairwise correspondences. Why is this useful? Well, you remember that we want to solve this problem of correspondence in an unsupervised manner, which means that we have no ground truth correspondences or anything like that to define how close two given poses are. And instead, as a heuristic, we use the closeness of the pairwise putative matches as a signal that tells us how close the two poses are, with the rationale that a low matching score, a low matching energy, tells us that the poses are very close to each other. Using this information, we then define a symmetrized version of this energy as our final affinity scores between two given pairs, so that we, in the end, have an edge-weighted but an undirected graph. Right, so for our shape collection, first of all, we define these affinity weights between any pair of poses, which then effectively defines a graph structure on our shape collection where the edge weight between any two poses is simply equivalent to the affinity score. Now, the final component of our method is the multi-shape matching part. And we do this by simply saying, okay, we defined the affinity scores such that a low score corresponds to very similar shapes that have a very accurate pairwise match. Now, we will leverage this information by simply saying that the final multi-shape correspondences are defined as the shortest path within our given shape graph. And yeah, again, this means that usually edges along this shape graph tend to correspond to very accurate pairwise matches. And by concatenating matches along the shortest paths, we end up with very accurate multi-shape correspondences. During training, we will enforce cycle consistency, and I will cover this in a second. Right, so to just look at an example for the teaser example, if we take two pairs, then we see that the shortest path on the right side is much more accurate than the putative input. So in our architecture, we essentially append this multi-shape matching as an additional module. This will serve for once to, at test time, compute more accurate multi-shape correspondences. But also we have a feedback loop here at train time where the cycle consistency loss improves again the pairwise matches through the by enforcing consistency between the multi-shape correspondences and the pairwise correspondences. To show some results, first of all, we evaluated the method on data sets with topological changes. These are for once Shrek isometry and the top kits data set, where we show state-of-the-art performance. Here are some examples. So again, we see that there's a lot of places of self-contact in these kind of benchmarks. And in all of these places, our method tends to perform much more accurately. And this is largely done by the fact that we look at the whole shape collection and infer something about the latent topology. We also evaluated the method in terms of interclass matching, which means that we have a collection of inhomogeneous shapes with different poses, and we again show very good performance. Also, on the right side, we visualize the learned shape embedding. Right, so to conclude, we introduced this notion of the shape graphs and the affinity scores, and based on this, define multi-shape correspondences in terms of shortest paths. And we show state-of-the-art performance. So yeah, feel free to come to our poster for more discussions. Thank you.